Hello, and welcome to the video of our paper, Revisiting Local Computation of PageRank, Simple and Optimal. I'm Mingji Yang, and this is a joint work with Hanzhi Wang, Professor Zhewei Wei, and Professor Jirong Wen. We are from Renmin University of China. So let me start with the problem formulations. As you know, PageRank is a famous node centrality measure on graphs. It assigns a global importance score to each node on the graph based on the graph structure, and PageRank is a special and celebrated form of random walk probability on graphs. Historically, PageRank was proposed by Google in 1998 for ranking web pages in their search engine, and it is also considered as one of the top 10 algorithms in data mining due to its importance. Next, let me introduce the definition of PageRank based on a notion called alpha walks. Here we involve an extra parameter called the damping factor, denoted by alpha, which is a real number between 0 and 1. And in each step of the alpha walks, the walk may simply terminate at the current node with probability alpha, and otherwise it will move to a random out neighbor of the current node, just like a classic random walk on graphs. So this is equivalent to saying that the length of an alpha walk is a random variable which follows the geometric distribution with parameter alpha. So next, we define the PageRank score of node T, denoted by pi t here, as the probability that an alpha walk from a uniformly randomly selected source node in the graph terminates at exactly the node T. So as an example, here is a possible outcome of sampling a source node uniformly at random and performing an alpha walk from it, which terminates at node 8. So as you can see, alpha walks can be understood as a type of short random walks on the graph, since its expected length is 1 over alpha. And in this work, we will consider alpha to be a constant. Also, to ensure that alpha walks are well defined on the graph, we will assume that each node on the graph has a non-zero out degree. Okay, now let me introduce the central problem considered in our paper, that is single node PageRank estimation. In this problem, we are given a single target node T on the graph, and our goal is to estimate the PageRank value pi of T within constant relative error with high probability. So this is a very basic problem in PageRank computation, and it has also been studied for many years. And in this work, we investigate the worst-case complexity of this problem for an arbitrary target node T on the graph on an arbitrary directed graph. And of course, it is well known that a typical iterative algorithm can compute the whole PageRank vector in near linear time with small errors. So what is interesting here is to consider local algorithms with sublinear complexity. Different from the traditional settings where the entire graph is given as input to the algorithm beforehand, here the algorithm in question is only given the target node T on the graph as input, and so at the beginning it is completely unaware of the whole graph structure. However, the algorithm can perform local explorations to detect the subgraph near T like this. So this setting potentially allows the algorithm to estimate the PageRank value of T in sublinear time. And we also allow the algorithm to perform a jump operation, which returns a uniformly random node in the graph. So the algorithm may possibly jump to a node that is far away from T and also perform local explorations from this node. Formally, the model of computation under our consideration is the real-run model with access to a graph oracle. And specifically, the graph oracle can help the algorithm to learn at unit cost the in degree or the out degree or a specific in neighbor or a specific out neighbor of a given node on the graph. And also, as mentioned, the Oracle also allows a jump query, which returns a uniformly sampled node on the graph. And this also takes unit cost. Following previous works, we call this setting the arc-centric graph access model. Well, in our work, we also consider a highly relevant problem related to a notion called PageRank contributions. Here, a node S's PageRank contribution to node T, denoted by pi over St here, is defined as the probability that an alpha work from S terminates at T. Recall that the PageRank value of T is defined in a similar way, but from a randomly selected source node on the graph. So it is straightforward to see that the PageRank value of node T equals the average of all nodes' PageRank contributions to node T. And this is why the value of pi SD is called the PageRank contribution of S to T. Well, for PageRank contributions, we consider the following problem called detecting the delta contributing sets of T. In this task, we are given an individual target node T and also a parameter delta, which lies between 0 and 1. And we want to detect the set of nodes that contribute at least delta fraction to the node T's PageRank score, as expressed in this formula. Well, in this video, we will give our results for this problem, but we are not going to talk about the details. Next is our results for these two problems. First, let me discuss some previous results for single-node PageRank estimation. The first one worth mentioning is an algorithm called BiPPR proposed by Lofgren et al. In 2016. However, they did not give a meaningful worst-case upper bound of BiPPR, and instead they considered the average case upper bound and give it as O, the square root of M, for an average choice of the target nodes. Here, M denotes the number of edges in the graph. Note that although this average case upper bound is fairly small, it cannot hold in the worst case, as indicated by the lower bounds known afterwards. For the worst case upper bound, the first fully sublinear one was given by Bresson, Peserico, and Prato in Fox 2018, where they gave complicated algorithms and analysis to give an upper bound of soft O, the minimum of n to the 3/4, delta to the 1/4, and n to the 5/7, m to the 1/7. Here, the notation n denotes the number of nodes in the graph, and the delta denotes the maximum out degree of the graph. They also gave a lower bound for this problem of this one, where the exponents over n are 1/2 and 1/3 respectively. Note that here, smaller exponents over n indicates smaller bounds. And later, recently, this upper bound is further improved by the same authors in 2023 to this one, where the exponents over n are both decreased to 2/3. However, as you can see, there still exists a polynomial gap between the upper and lower bounds. And our results bridge this gap by tightening both the upper and lower bounds, showing that the worst case complexity of single-node PageRank estimation is the minimum of n to the 1/2, delta to the 1/2, and n to the 1/2, m to the 1/4. And surprisingly, we derive our upper bounds by showing that the known algorithm BiPPR had already achieved this optimal upper bound. And in our paper, we actually give some more bounds involving delta in, the maximum in degree of the graph. For upper bound, this will further incorporate a term of n to the 1/2, delta in to the 1/2. But for the lower bound side, the things are getting a little bit more tricky. For the simpler case, when the minimum of delta in and delta out is fairly large, that is omega n to the 1/3, we are able to derive a completely matching lower bound. But if the minimum of n is smaller than n to the 1/3, we derive a matching lower bound up to subpolynomial factors, where the exponents differ by an arbitrarily small positive constant. And on the other hand, for the problem of detecting the delta contributing set, we are able to give completely matching upper and lower bounds. That is, the minimum of delta in, delta out, and the square root of m over small delta plus a term of m. Next are the detailed techniques for deriving our results. Our techniques and analysis are generally simple. The key ingredients of our deriving our upper bounds are the known approx contributions algorithm. It was first proposed jointly by Anderson, Box, Trias, Hopcroft, Miragni, and Teng in 2007. And until now, it has become an algorithmic cornerstone for random walk probability estimation, being used in a variety of tasks. However, despite all years' efforts, its worst-case complexity has not been fully understood. Overall, approx contributions receives a node T as input, and it approximates PageRank contributions from all nodes to the target node T. And it does so by performing several local pushback or simply push operations to propagate the probability mass backward along incoming edges. And in this work, we derive a new and tight upper bound for the complexity of approx contributions, which has remained undiscovered for years. And actually, BiPPR has found an elegant way to combine approx contributions and Monte Carlo sampling, which is a basic technique in designing sublinear time algorithms. BiPPR uses the invariant property of approx contributions to construct a low variance bidirectional estimator, and this estimator can be sampled by simply generating alpha walks in the graph. In this work, we also revisit BiPPR's error bound and complexity with the help of the new bound of approx contributions. Here are some intuitive explanations for the rationale behind BiPPR. First, consider the typical Monte Carlo method for estimating single-node PageRank, where you generate a bunch of alpha walks in the graph and calculate the fraction of these walks that terminate at t as the estimates for pi of t. However, in this graph, this method would require omega n time to touch t at least once using Monte Carlo samplings because of the large out degree of the intermediate node. So this would potentially require linear time. However, as you can see in this graph, you can simply travel backward from t to find the intermediate node u. So in this way, the goal of the Monte Carlo samplings switches from touching the target node T to touching the intermediate node U, so that the variance of the estimator can be dramatically reduced. On the other hand, for lower bounds, we construct a family of graphs containing a small and hard-to-detect subgraph that largely determines the magnitude of pi t. And the difficulty to detect the subgraph comes from detecting an unseen parent among many explored parents. Let me explain using this graph. We will construct the graph so that the special node V is important to the PageRank value of node T. However, to detect the node V through local explorations from node T, the algorithm has to examine essentially all these a bunch of edges drawn here. This is because even if the algorithm has inspected all these wrong parents through the parents of U3, it has to inspect them again when examining the parents of U2, because the algorithm cannot determine which of these parents are the special node V beforehand. Okay, let's further go into the details. The algorithm of approx contributions relies on a push operation, which maintains two variables for each node on the graph. One is the reserve, denoted by P of U, representing the known probability that an alpha walk from U will terminate at node T. And the other is the residue, denoted by R of U, standing for the remaining probability that an alpha walk at U will further travel to node T. Initially, the algorithm will set all these quantities to be 0, except that ROT is equal to 1. And in a push operation to an arbitrary node V in the graph, the algorithm will perform 3 steps. It will first convert V's residues to its own reserve. That is, we increment the reserve of V by alpha times the current residue of node V. The second step is to convert V's residue to the residues of its in-neighbors. For example, for V's in-neighbor U1, its reserve will be increased by 1 minus alpha times RV divided by the out degree of node U1. And finally, it will reset T's residue to 0. Well, actually, this single step, single push operation corresponds to a single step in the typical iterative approach for computing PageRank contributions, but it does so in a node-wise and local manner. A very important property of approx contributions is called the push invariant. That is, this equation is maintained through the push operations. It says that for each node S in the graph, the value of pi st equals this summation plus the reserve of node S. Here, the reserve represents the known probability that an alpha walk from S terminates at T. But for the remaining probability, it is expressed by this summation. It sums over all the nodes U in the graph, and it multiplies each value of pi Su by the value of residues R of U. It represents the probability that an alpha walk from S will travel first to the node U1 and then to the node T. And this invariant is designed for the value of PageRank contribution, pi OST. And by averaging it over all nodes S in the graph, we can obtain an invariant for PageRank. And by substituting the pi of U here by the random variables chi of U, which stands for the indicator variable of the event that an alpha walk from a random node in the graph terminates at U, we will obtain a bidirectional estimator. And this leads to the process of the bi-PPR algorithm. Its process is divided into 2 phases. The first phase is exactly the approx contributions algorithm, and the second phase is Monte Carlo sampling. In approx contributions, the goal is to reduce the residues of all the nodes to be below a parameter epsilon. So, as long as there exists a node V in the graph whose residue is larger than epsilon, the algorithm picks such a node and performs push operations on it. And in the second phase, bi-PPR generates NR samples of the bidirectional estimator, and then it returns the average value of these samples as the final estimates for pi t. To analyze the complexity of bi-PPR, it is essential to analyze the complexity of approx contributions. This complexity can be bounded by this summation over all nodes U in the graph, where the summand is the number of push operations performed at U times the cost of performing a single push operation to it. And one can show that this can be upper bounded by this expression by using the properties of the push operations. Here it is 1 over alpha times epsilon times summation over U, where the summand is the PageRank contribution of U to T times the in degree of node U. A key observation in our work is that we find that CC expression can be bounded about by O n times the PageRank value of T times the minimum of the maximum outer degree of the graph and m to the 1/2. Let's first see how these new bounds of approx contributions can lead to our claimed bound of approximating single node PageRank. Recall that the complexity of BiPPR can be divided into these two parts. The first one is the cost of generating alpha random walks, which can be derived by analyzing the variance of the bidirectional estimator in BiPPR. And the second one is our new bound of approx contributions. So here, the parameter epsilon is to be determined by BiPPR. And it is not hard to see that when the two expressions are equal, the overall complexity of BiPPR can achieve the minimum value, which is exactly the claimed upper bound for single node PageRank estimation. And although we cannot know the optimal value of epsilon, this complexity bound can still be achieved by adaptively trying a sequence of halving settings of epsilon. Okay, now it remains to prove our upper bounds on this summation. For the upper bound involving the maximum outer degree, we first split the in degree of node U into a summation over the in neighbors of the node U, where the summand is a number 1. And this can be converted into a summation over all the edges in the graph. Now we reorder the summation and multiply the summand by the outer degree of node V and also divide it by this factor. So the inner summation here is over the out neighbors of node V, and the summand is pi ut divided by the outer degree of node V. So using the definition of PageRank contributions, we can show that this inner summation is upper bounded by the PageRank contribution of V to T divided by 1 minus alpha. Further, we upper bound the outer degree of node V here by the maximum outer degree delta, and simplifying this expression would lead to this upper bound. On the other hand, for the upper bound involving m, we start from the green part here, and we split the term of pi ut into two terms of the square root of pi ut, and we multiply the first one by the square root of the outer degree of node V, and divide the second one by it. And so we can apply the Cauchy-Schwarz inequality to upper bound this by the product of these two summations. Reordering the terms would lead to this expression. Now for the inner summation over the in neighbors of node U, we can see that it is the summation of the outer degrees of different nodes, so it can be upper bounded by m. And for the second summation, once again, we can upper bound it by pi vt over 1 minus alpha. And finally, simplifying these expressions would lead to the desired upper bound. This actually completes the whole proof for all our upper bounds. And finally are the conclusions. In this work, we derive matching upper and lower bounds for single node PageRank estimation and detecting the delta contributing sets. We showed that the known algorithms of BiPPR and approx contributions are already worst-case optimal. Let me end this video with some open problems. First, it may be possible to extend our results to other queries or measures based on random walk probabilities. The second one is to consider non-constant alpha because we consider the damping factor alpha to be constant here. And lastly, it may be meaningful to consider settings beyond the arc-centric graph access model because our lower bound seems to show a limitation of this classic model. That's all for the video. Thank you.